And so so what's the introduction to the course? Well, I'm going to do group cohomology first, look for arbitrary groups, and then settling in on finite groups, a little bit of group homology as well. Then we will settle into cohomology of profinite groups, which is essentially the same as Galois cohomology. Then we'll do local class field theory. Then we'll do global class field theories. That's kind of my overview, you know. And what is class field theory? Class field theory is some mechanism for understanding the Abelian Galois extensions of a field using data internal to the field itself. So that's kind of the slogan of class field theory. So it's some kind of it's some kind of useful systematic procedure for studying finite Abelian extensions of a field. There are several classes of fields for which class field theory is known. And so the ones that we'll talk about in this class are for local fields. So that's a complete discretely valued field with finite residue field. So either a p-adic field, finite extension of QP, or a Laurent series field over a finite field. Those are the local fields for which we'll do local class field theory. That can be slightly generalized if you really want to, but I don't think that we do. And then class field theory for global fields, and as ever, a global field is either a number field or a function field in one variable over a finite ground field. Okay, and so in particular, we get a good description of the Galois group of the maximal Abelian extension of such a field. Okay, so that's what class field theory is. If again, probably if you're taking the class, it would be nice if you'd already had some you've heard class field theory come up in various contexts. It's certainly very useful. It comes up all over the place in algebraic number theory and arithmetic geometry. I suppose if you ask me where class field theory comes up, I would say that it comes up in particular when you study the theory of complex multiplication, of elliptic curves, of Abelian varieties, or even of Drinfeld modules, some recent work of mine. So class field theory in the global field, in the positive characteristic case. In fact, Drinfeld modules were invented, I think, among other things, to give explicit class field theory in the function field case. Okay, so that's all I have to say about class field theory in terms of general organizing remarks. But does anybody have any questions about that or where we're going? No? Okay. Yeah. So I think we're just going to do it. All right. So let's get into it. Okay. Right. So let me begin. Just a couple of, so that I'm following Harari. I'm going to diverge a little bit shortly and for the first 2 or 3 lectures, but here I'm just making some comments about, he has some just like notational remarks at the beginning, and they're a little French. So they're translated to English, but they're still a little French somehow. And so let me translate them further. So he says filtered limit, direct limits will be filtered limits. That's a slightly French thing to say. Most people in English would say that that you have your partially ordered set is directed, okay? Which means that if you have any 2 elements of your partially ordered set, there's a third element that is greater than both of them, greater than or equal to both. Okay, and yeah, and so he mentioned I guess he says a little bit about tensor products. I forget what he said. Maybe this just reminded me or inspired me to say something. So briefly in our course, I suppose it's not the most critical thing in the world, but we will meet a tensor product. Maybe I should step back and say in this is not a course where all rings are commutative. Okay, so we've had a good streak, you know. of courses where all the rings were commutative rings. And in this course, the most important, as we'll see, I guess, in the second lecture, the most important ring for us is going to be the group ring, the integral group ring attached to an arbitrary group G, okay, which is commutative if and only if the group is commutative. And okay, and so if you're doing Galois homology, then the group is not going to be commutative. So here, ring means ring with a multiplicative identity, as always, but not necessarily commutative. Okay, and so you have to kind of reorient yourself a little bit if you're used to working with commutative rings. So of course, once the category of left modules over a totally arbitrary ring is still a very nice category. It's an abelian category with enough projective objects and enough injective objects, which will be of use to us. Let's see. Right, and so the point though is that a tensor product of modules over non-commutative rings is more of a production than tensor products in the commutative case. And so let me kind of review that just a little bit. So first I'll give you a reference. Jacobson's Basic Algebra 2 is a usually excellent reference on whatever is in it. So section 3.8 is these non-commutative tensor products. And so the natural setting for that are what are called bimodules, which are useful in and of themselves. Right, so what's a bimodule? If you have two rings, no commutativity assumptions in sight, an SR bimodule is a commutative group M, which on the one hand has the structure, on the left hand, has the structure of an S module, and on the right hand has the structure of a right R module, okay? So two hands. And then, of course, we want these structures to be compatible with each other. So for all S and S, X and M, and little r and R, basically, if you act on the left by S and you act on the right by R, this looks like an associativity condition, but if you think about it, it's really more like a commutativity condition. It says if you act on the left by S first and then act on the right by R, that's the same as if you act on the right by R and on the left by S. Okay, so you see that if the rings were commutative, this would be this would be more automatic. Okay, but so that's what a bimodule is. Okay, so that comes up. And then just a few brief comments. So any ring, commutative or not, is an RR bimodule. Okay, so you have the ring acts on itself on the left. It also acts on itself on the right. This lovely identity is called the associativity of multiplication in the ring. Okay, and so yeah. Okay. What if you only have a one-sided module and you want a bimodule? Don't worry. So any left S module is automatically an SZ bimodule. Okay, just because a commutative group is a Z module, so you have that for free. And then on the other hand, any right R module is automatically a ZR bimodule. Okay. Why am I mentioning this? I'm mentioning this because, as we'll see in a bit, we want to do a tensor product over group rings. And so again, I will define the group ring from scratch a little bit later. So I guess this is just a bit of a preview. Yeah, so I guess what you need to know at the moment is that to every group, there's attached this integral group ring. And then there's a lot of nice punctoriality properties. In particular, whenever you have a homomorphism of groups, that will induce a homomorphism, kind of easy homomorphism of group rings. If H is a subgroup of G, then the group ring over H will embed as a subring of the group ring over G. So what? As we'll see in the second lecture, we will be dealing with modules over the group ring all the time. So suppose we have a ZH module, and we would like to define in some way an induced, quote unquote, ZG module. Okay, so is there some canonical way that we can get ourselves from a module over this smaller ring to a module over this bigger ring? Well, in commutative algebra, if I said that, you'd be like, hey, why don't we take the tensor product, right? And so that's what we do here. We just have to do it carefully. And this induced is both, reasonable English usage and a technical term. So this is literally the induction from H to G. So that's a fundamental object in group homology, group cohomology, and representation theory. Okay, in representation theory, it's like the most important thing somehow. So the induction is you do this. You take ZG tensored over ZH of M, and now you have to like stop and think that this makes sense. So ZG was a ZG bimodule, and so okay, if you're a right module over a ring, then you're also a right module over every subring, right? Right. So ZG is a ZG-ZH bimodule. What about M? Well, M was a left ZH module, but as I said, therefore it's a ZH-Z bimodule, okay? And the way you think about tensor products and bimodules works is, oh, did I manage not to say this in general? That's weird. Yeah, for some reason, I think I didn't write down the general case. Let's see if I can squeeze it in here. So it's sort of a bit like matrix multiplication. If you have rings, RS and T, or rings, okay, and you have M, which is an RS bimodule, and you have N, which is an ST bimodule, okay, then you can take M tensored over S with N, and then somehow that tensor product kind of uses up the S in the middle, and this becomes an RT bimodule. Okay, so this is what I'm not proving anything. If you look in the discussion on non-commutative tensor products, okay. So you see that you see in some formal sense it's kind of like matrix multiplication, right? In order to take the tensor product, we need the middle indices to be the same, just like we need the middle indices to be the same in order to multiply two matrices, and then the middle guy, kind of goes, it's been a long time, but I think this does have something to do with matrix multiplication. Exercise, what does this have to do with matrix multiplication? Something. Pretty much everything has something to do with matrix multiplication. Okay, so yeah, so that's what happens. And so here, if we do this, then we take this tensor product, and you see the ZH, we can do this because we have a bimodule where the second ring is ZH, and here we have a bimodule where the first ring is ZH, so we take the tensor product, and they go away, and then we're left with a ZG-Z bimodule, which is the same as a left ZG module. Okay, so we'll talk about this in more detail. It's in this. By the way, you really don't need the general theory of tensor products of modules in order to define this. We'll talk, the case of taking a ZH module and tensoring up to ZG is a little simpler than that, and so we can talk about that later. Anyway, so for some reason, whatever Harari writes before his text starts inspired me to talk about bimodules. Okay, other silliness, just some terminology. I haven't even read enough specifically to see where this is used yet. So for him, compact means quasi-compact. So for a topological space, of course, right? So if you have a topological space, compact means that every open cover has a finite subcover together with Hausdorff. So that's the Bourbaki/algebraic geometer convention. I happen to agree with it. So in my general topology notes, which I just added some to because I just taught general topology, that is actually my convention. So I'm fine with compact including Hausdorff. But look what he does next. He says that locally compact means every point admits a compact neighborhood and Hausdorff. If you stopped right there, I would agree. So my definition of locally compact, it also includes Hausdorff, and then every point should admit a compact neighborhood. Together with the Hausdorff property, Tyler knows this because he was grading for my topology class. Yeah, so locally compact, together with the Hausdorff property, if you have one compact neighborhood, then you have a neighborhood base of compact neighborhoods. Okay, but for some reason, he also adds this condition countable at infinity. And I mean, come on, right? Like words mean things. You can't just sneak everything in, So, but what the F does countable at infinity actually mean, right? I should stop and ask. I guess I screwed it up. I should stop and ask people if they know. This is again a Frenchism, I think. Like it mostly appears in English that's been translated from French. In English untranslated, maybe it is. Anyway. somehow translated from French. You find, anyway, in French texts, they tend to use countable at infinity. In English, one says sigma compact, which still, what does that mean? It means it's a countable union of compact subsets. Okay, so like in measure theory, sometimes you see sigma compact. Why are we calling sigma compact the same as countable at infinity? I'll get the general topology out of my system in like another week or two, probably. It's still a little there. So the exercise is part A. Were there more parts? Anyway, so the exercise here, you don't have to do this exercise. If you're locally compact and second countable, so there's a countable base for the open sets, then that implies that you're sigma compact. Okay, so that's important because that means probably most of our spaces are going to be second countable anyway. And so if it's second countable, then this ride-on is automatic. And then, but why are we calling it countable at infinity? Well, okay, so let's say a Hausdorff space is hemi-compact. I didn't make this up. This is actually a term. If there's a sequence of compact subsets such that every compact subset is contained in some element of the sequence. Okay, so you think about this, I mean, points are compact, so this certainly implies that it's a hemi-compact space is most certainly sigma compact. Okay, so it's stronger. In fact, a topological space is hemi-compact if and only if its one-point compactification is first countable at infinity. Okay, so it has a countable neighborhood base. And so what's the point of this? This, I think, is where the term countable at infinity comes from. In general, hemi-compact, however, is stronger than sigma compact. So this is a little bit dangerous. Okay. However, if you are locally compact, then sigma compact and hemi-compact are the same. Okay, so to say that a locally compact space is a union of countable union of compact spaces, to re-express that condition as countable at infinity is reasonable because under the assumption of local compactness, it is equivalent to having a countable neighborhood base at infinity. This may never come up again. we'll see. All right. Yeah, general topology. Okay. So for a field K, he denotes overline K by a separable algebraic closure. I'm totally fine with that. I've done that in some papers. Okay. All right, let's get started. Are there any questions? Oh, I did want to say one thing before we get started. We are going to use some homological algebra in this class. I guess it says that in the syllabus, I guess, but I hadn't mentioned it yet. What I want to say is that if you wanted to take the class, then hearing that shouldn't change your mind. If you've already had homological algebra, great. Homological algebra is taught at UGA every 2 years at least, occasionally every year. So you can take it. Wait, is that happening now? Yes.
Yeah, I think Dr. Bo's teaching it.
Yeah. Okay. So maybe you'd like to take homological algebra, but there's a it's not a could only be a good thing. So okay. So even better. You can take it concurrently, I guess. But to be really honest, you can use homological algebra without having taken a whole course in homological algebra. Like, let's be real. Sometimes we need to use things that we haven't studied in complete generality. It's better if we can learn it. So yeah, and so I guess what I'm trying to say is that if this course is your first exposure to homological algebra, if you're taking this concurrently with homological algebra, that would be great because then the details will get filled in, and you have some nice motivation. But even if you take this course and you're like, all right, well, I learned how to fake my way through some homological algebra, and then at some point in the future, I should really learn about all these derived functors and delta functors and long exact cohomology sequences and the whatnot, then great, it's a good impetus. But yeah, so I mean, I really think that I just think that in practice, yeah, sometimes you have to kind of take certain things as for granted. understand them superficially and then come back later if necessary. So okay, we'll see how much. I think most of the homological algebra that we're going to use is pretty general nonsense, stuff, and so it's not. I don't think the deep theorems of this course are going to be proved by homological algebra, not as I recall, anyway. It's more of like a setting things up. Okay. All right, so let's get started. So let G be a group, okay? And again, for me, it's not necessarily finite yet, although Harari imposes the finiteness condition. Again, there's a good reason for that. But let's start with a totally arbitrary group. So today we'll talk about what a G module is. So a G module, first of all, is a Z module, so otherwise known as a commutative group, endowed with a Z-linear action of G. Okay, so what's a Z-linear action of G? It's an action of G by Z-module automorphisms of M. Okay, so it's a map from G into the automorphism group of the additive group of M. Okay, so that's slightly fancy. But this is as fancy as saying that a G set is a homomorphism from G into the group of bijections of the set X. Okay, it's like an equivalent level of fanciness. And so again, you can unpack that definition. So of course, otherwise put, you can think of this as being a map from G cross M into M. I didn't write that, but all right, I'll write that. Right. And you apply G, and then an automorphism eats an element of M and spits out another element of M, so you can't really argue with it. And what should it do? Of course, it should it should preserve the additive structure, and it should be homomorphic. Okay, so not a problem. So a G module is indeed a Z-linear action on your set. Okay. All right. So we have the notion of a homomorphism of G modules. So it's just what you would think. Again, it's the linearized notion of a homomorphism of G sets. So you have a Z module map, so just a homomorphism of abelian groups from, you got me to say it. You have a homomorphism of commutative groups from M to N that commutes with the G action. Okay, so for all little g and G and for all little m and m, if you apply F and then act by G, that's the same as if you act by G and then apply F. Okay, so again, that's what a homomorphism of G sets is, right? Okay, great. Really great though. So now comes the whirlwind homological algebra, but we'll understand this better in the next lecture. So by G mod, I mean the category of G modules. So they do form a category. I just told you what the objects were and what the morphisms were. It's not just any old category though. It's the type of category that the homological algebra pounces on. Okay, so it's an abelian category. I'm not even going to review what that means. Okay, I think, oh, by the way, I think there is, I think, there is an appendix on homological algebra in Harari's book. I actually, myself, I taught homological algebra a while ago, so I have some lecture notes on homological algebra myself, so I've just kind of been looking at my own lecture notes. But yeah, so there is an appendix on homological algebra. That should be helpful. Again, if you don't know what an abelian category is, you should think of an abelian category as some kind of formalism of the notion of the category of modules over a ring, where you can do a lot of the main constructions. Things have kernels, things have co-kernels, you have short exact sequences, you can define projective and injective objects. That's how an abelian category works. The actual definition is some category with some kind of additive structure. The Hom sets are equipped with, I don't want to do it. Okay, so there's an abelian category that satisfies some very reasonable axioms. Moreover, it has enough projective objects. So I'll review what a projective object is in this context when I need to. But so to have a bit, yeah. Now's a good time. So we have short exact sequences. right? So in an abelian category, we have a notion of short exact sequence. Okay, that's part of the formalism. And to say that, I mean, again, there's lots of ways of saying it in specific categories, but for us, projective means that this short exact sequence admits a section. So if this map is Q, then so P is projective if for all short exact sequences terminating at P, there exists a section sigma from P to N. What does that mean? It means that sigma composed with Q is equal to the identity map on P, and that also implies that the sequence splits. So implies that N is isomorphic to M direct sum B. Okay, so an object is projective if every time you realize P as a quotient by modding out by something, then P also lives inside N as a direct sum. Okay. Right. Okay. So that's what a projective object is, and then dually there's a notion of injective object. Okay. Why not? So the injective object at this categorical level literally is the dual. I'm just going to reverse all the arrows from up here. And so I is injective if for some reason I don't want to call it sigma anymore, but I don't care. Alpha. Okay. So again, if the other way around, so if there exists alpha, cosection or whatever the word is, from N to I, such that what? So such that so just exactly the other way around, and therefore again, N is isomorphic to the direct sum. Okay, so an object in an abelian category is injective if whenever it sits as a sub-object of something, then it's actually a direct sum. All right. So, right. Okay. So I claim to you, and I will explain why in the next lecture I mean, I won't really prove it. I'll explain why we should already know that it's true. So the claim here is that the G modules form an abelian category that have enough projective objects and enough injective objects. Okay, so to spoil it just a little bit, in the next lecture, I will identify the category of G modules with another category that, we will have to agree to take as known from algebra that it is an abelian category and has enough projectives and enough injectives. And what categories do you know are abelian categories and have enough projectives, enough injectives? If you have a guess, your first guess is correct. Okay. All right. So what's the point, though? The point is that now we love to see these half-exact functors. If I have again, I'll review this. Will I? We'll see. I don't want to spell everything out right now. If I have a right exact functor, let's say into the category of abelian groups, just to fix ideas, because that's what it's going to be, then we can take its left-derived functors and get a homological delta functor. So this is part of the homological algebra that we're faking. You may want to look this up in the appendix of Harari's book or elsewhere. And then if we have a left exact functor, then we can take its right-derived functors and get a cohomological delta functor. Okay. So if I'm telling you this, then we should be looking for, where's my right exact functor? Where's my left exact functor? By the way, if your functor is exact, which means it takes exact sequences to exact sequences, well, then you don't need to do this because these derived functors will all be for n greater than or equal to 1, all of these derived functors will be 0. So somehow these derived functors are, if your functor is exact, then it takes let's say a short exact sequence to a short exact sequence. If your functor is left exact or right exact, it does not take a short exact sequence to a short exact sequence, but there's an associated long exact homology or cohomology sequence. Okay. So, right. And let's see, little comment here. So a sequence of G modules, again, I've skimped a little bit on the definition. So what do I mean for a sequence to be exact? In fact, it's exact if and only if the underlying sequence of Z modules is exact, okay? So the kernels and the co-kernels and all that are just computed in the category of Z modules. All right. A fancy way of saying this is that there's an evident forgetful functor from the category of G modules to Z modules, where you literally just forget the G action. And what I'm telling you, what I just said, is that that forgetful functor is exact. Similarly, if you took a subgroup H of G, then you could forget that you have G module structure and remember only that you have H module structure, and that will still be an exact functor for any subgroup. Okay. And again, I think there's some homological abstract nonsense later. Maybe you don't need to worry about it now, but if some kind of functor is anyway. So if I were ever to look at the adjoint functor of an exact functor, then some nice property would happen. So we'll see later. Okay. All right. So now the question though is that, okay, this is a lot of general nonsense. What are we actually doing here? You know, like, are we doing homological algebra? Okay, well, shouldn't you be giving me a functor which is right exact, probably not exact, and a functor which is left exact and probably not exact? Yes, I will give you two such functors. Okay, so this is where it starts. So for a G module, we can define the invariants M super G. So this is the collection of elements in M such that Gm is equal to M for all G and G. Okay, so it's exactly what it looks like. It's the elements that are pointwise fixed by the group. Every element of the group acts trivially. Okay, so it's easy to see that this set of elements is a Z submodule. If you're pointwise fixed, the sum of two things that are pointwise fixed is also pointwise fixed. The inverse of a thing which is pointwise fixed is pointwise fixed, no problem. So MG is a Z module. Every Z module is a G module on which G acts trivially. Okay, so maybe I should have said this already. Maybe I was going to say it later. If M is any Z module, can make it into a G module by having G act trivially. Okay, so there's a lot of G modules out there. Any commutative group, you know, it's not an interesting question which commutative groups or the underlying commutative groups of a G module. They all are. You know, the action could be trivial. Okay. And so MG, being the type of Z module on which G acts trivially, is a G module. It is a G submodule of M. Of course it is, because it's a Z module and G acts trivially. And it is nothing else than the largest G submodule of M on which G acts trivially. Okay. So this is called the module of invariance. Okay, and so the claim is that this is a left exact, okay, but generally not exact. So first of all, okay, now I'll tell you what this means. So left exact means if you have this much of an exact sequence, okay, 0 to M1 to M2 to M3. Note, I do not need to assume that the last map is a epimorphism, or whatever you want to call it here, surjective in our concrete context. If I just have M1 being injected into M2 and then you're exact at M2, left exact means after you apply the functor, you still have this much exactness. But even if you were to assume that this last map is surjective, you wouldn't necessarily get that the image after you apply the functor is surjective. So that's what it means for a functor to be left exact, but not necessarily exact. Exact would mean I apply the functor to this short exact sequence and I get another short exact sequence. Okay. So that's what I'm claiming. My claim is that taking the taking the G invariance as a functor from G modules to Z modules, and it is left exact, but almost never exact. Okay. So yeah, so the first exercise for you is to show the left exactness. Okay, there's not. I mean, you don't need to know anything. You just apply the definition. Okay, so I promise that. I mean, for instance, this one is completely trivial because M1G is living inside M1, M2G is living inside M2, and if I restrict an injection, then I get injection. Okay, so I already did some of the exercise, and now all you have to do is prove the exactness at this middle point here. Nothing on my sleeves. Okay, it's fine. Okay, but let me give you an example to show that that it is not exact in general. And so I wanted to give an example that I don't know, just kind of felt more like representation theory and like, you know, ordinary math. I wanted this example to like not look number theoretic in any sense for some reason. I just wanted to, yeah, group theory. Okay. Right, so what's my group? Yeah, I really wanted my example to be where M is a real vector space to indicate that like this can go wrong even if you have a real vector space. Okay, so what is G? G is, okay, not the world's nicest subgroup of GL2R, I admit. It's this, you know, this unipotent subgroup. These are the upper triangular matrices that have ones along the main diagonal. Okay, so this is a subgroup. By the way, it's easy to see that this subgroup is isomorphic to the additive group of the real numbers. Okay, all right. So that's a certain subgroup. Let's have M just be R2. Okay, and so you know, G is acting on R2 in the usual way that GL2 acts on R2. Okay, just matrix multiplication. And so what's my submodule is just going to be R cross 0, in other words, the span of the first standard basis vector. Okay. First, I guess I'm claiming that N is a G submodule. So let's check, right? If I just take XY and I act on it by 1A01, don't I get X plus AYY? I think I do. So what is this telling me? This is telling me that when is this XY vector going to be fixed no matter what A is? Yeah, it's necessary and sufficient for y to be equal to 0. If y is equal to 0, then no matter what A is, if I apply this matrix to x comma 0, I get x comma 0. Whereas if y is anything that is non-zero and A is anything that is non-zero, then it was not fixed. Yeah. So you can't really argue with that, I hope. And so right. So therefore, the fixed submodule of N is N itself, but N is also the fixed submodule of M. Okay. What about the quotient? Yeah, so what, yeah, so by the way, I have some, maybe I didn't write this down. So I have some short exact sequence, of course. 0 goes to M, goes to M, goes to M mod N, goes to 0. Okay, and so this is really just 0 goes to R, goes to R2, goes to R, goes to 0. Nothing fancy. Okay, what about the invariance of the quotient? Okay, so now what's happening? What's happening is that we're letting the matrix act on this vector, but we're modding out by M, which is really the first component. So therefore, we're really only looking at what the action does to the second component. Okay, and so you know, of course, the action on the second component, you know, the 0, 1 is not a G-stable subspace, but these things are G-stable modulo M, okay? And so you see, again, I could have written this out in more detail. I'll let you think about it a little bit. But of course, if this thing acts on any coset of X, then you really just look at what it does on the Y coordinate, and it doesn't change the Y coordinate. Okay? So my claim is that M mod N is also G invariant. Okay, so if we take the G invariance of this short exact sequence, 0 to N to M to M mod N to 0, I'll probably go to 250 today, by the way. If you have to leave at 240, no problem. We're recording it, we'll upload it, no problem at all. go at least to 250. So anyway, so we took the G invariants, and oh, there's the short exact sequence that I snuck in up there. And so then we take G invariants, and what do we get? Well, these are both n, and this map is, this was just an inclusion, so this map is the identity. And then this one is m mod n, but what was this? This was the restriction of the quotient map from m to n mod n to n. Well, if you restrict the quotient map to n, you get the 0 map. Okay? And then you look at this and you say, uh-oh, this map here was surjective, right? But now when I pass to invariants, by the way, these two things are isomorphic. They're both isomorphic to R, but the map is the 0 map. Okay? So this is an example where in particular, if I just look at the surjection from m to m mod n, so that surjection is surjective, and then if I take the G invariance on that surjection, then I got the 0 map. Okay, so this shows that it really is not right exact. Okay, so again, yeah, and so I don't know. I just think it's nice if the pathology is already evident. So by the way, like maybe we'll see later, you don't have to just do Z modules. If you had any commutative ring R, you could do you could do R linear G modules. So instead of the underlying guy being a Z module, the underlying guy could be an R module, and that would work just as well. And so here, this is the type of G module where the underlying guy is not just a commutative group, but is actually an R vector space. And that still messes it up. Okay. I will note here that the group G is infinite. Okay, so that'll come up later. Okay, so so we have a functor, namely passed to the G invariance, which is left exact and not exact. Well, that's great, because that's exactly the setting for which we can define cohomology, so the rate-derived functors. And so this is our first definition of group cohomology. So you do the homological algebra thing. And again, this is kind of like when I introduced the integral and I define it in terms of Riemann sums, and I scare you a bit. And then a couple lectures in, I introduced the fundamental theorem of calculus. So there's going to be a better way to compute these cohomology groups. But a priori, how do I define group cohomology? Well, I do the recipe of homological algebra. I have a left exact functor, which is not exact. So what do? I take an injective resolution. So m goes to E0, goes to E1, goes to E2, goes to E3. This is infinite, an exact sequence. Each of the E's are injective. Okay. If you having enough injective objects means that every guy can be, I don't want to use it can be monomorphed into, every guy is a subobject of an injective guy. And if you do that and you do some splicing, then you get an injective resolution. And then what do you do to get the cohomology groups? You apply the functor, okay? And then because the functor is not exact, once you applied it, you don't necessarily have an exact sequence anymore, but you still have a cochain complex. And if you take the cohomology of that cochain complex, then that is the group cohomology. So by our first definition of the group cohomology of G with coefficients in the G module n for any non-negative integer n, it is the nth cohomology of this cochain complex that I get by stripping away m and applying the functor. Okay, and by the way, this is precisely what the recipe that homological algebra tells us to do. Okay, so this is where if you've never seen this before, flip to the appendix and look up how well, what's the word for this? Right-derived functors. Okay. So these are the right-derived functors of the left exact functor. Okay. So yeah, so we take this, we take our injective resolution in the category of G modules, we take each of the G invariants, then we get a cochain complex, which just formally we have a bunch of these things. I guess the only content here is that the composition of any two of them is 0. And then the nth cohomology group is the kernel of the nth one modulo the image of the n minus first one. Okay. That's homological algebra. And then again, through the miracle of homological algebra, these right-derived functors form a cohomological delta functor. What a mouthful. That means, again, if the functor of G invariants had actually been exact, if I started with a short exact sequence, did I not write that? Where's my short exact sequence? Here's my short exact sequence that I'm starting with. So if I start with the short exact sequence of G modules, if the functor was actually exact and I took G invariants, I would still just get a short exact sequence of Z modules. I just showed you an example that it's not right exact in general. So it gets more interesting, but there's still something. So the failure of exactness of this associated sequence is measured using all of the cohomology groups. Okay, so you have this connecting homomorphism delta, then you get an H1 into M1, into M2, into M3, then you get another connecting homomorphism and into, okay, so this short exact sequence induces a long exact cohomology sequence. Okay. Again, that's just very, very mainstream homological algebra. And then, yeah, maybe this is an exercise or something. Can you figure out what what the so in this particular example, what's the point? The point is that we saw that we did not get exactness here, right? And so therefore, if we have this sequence, we're right here, and we just said if this map were the zero map, that would be equivalent to this guy being surjective. It isn't. Therefore, H1G of n must be non-zero in order for the surjectivity to fail. So it's got nothing to do with class field theory or anything, or Galois cohomology or anything like that, but you might want to ask yourself actually what this cohomology group is in our example. Okay. Right, and I remind you that I just told you that Gmod is an abelian category. I haven't proved it for you yet. Again, we'll reveal in the next lecture why that's happening. Okay, and then we can go the other way. So I gave you a left exact functor that was not exact, and then defined group cohomology to be the right derived functors of that functor. Actually, we can go the other way as well. So here is a different functor, okay, still from the category of G modules to the category of Z modules. Whereas MG was the largest invariant submodule of G, we can also associate the largest invariant quotient module of L. Okay. So what is that? So if you think about it, how do you form an invariant quotient? Well, in any invariant quotient, g of x has to be equal to x, right? If the action of g is trivial, then gx equals x. That's what triviality means. And so if we want that to happen in the quotient, then we should mod out by the corresponding relations, okay? So if you mod out by the z submodule will be a g submodule, so that's enough. So if you mod m out by the z submodule generated by gx minus x, as you range over all g and g and all x and m, then once you impose those relations, then again, that is a sub G module, easy to see. And so once you mod out by those relations, then you get then you get the quotient is invariant, and it's kind of clear, I hope, that this is the this is the smallest thing we could possibly have modded out by in order to get an invariant quotient. And so therefore, this m sub g is the largest quotient of m on which g acts trivially, whereas m super g was called the module of invariance. M sub g, unfortunately, maybe is called the module of coinvariance. Okay. And let's see. So again, now the claim is that if I take coinvariance, then this is right exact, but generally, usually not exact. Okay, so what does this mean? This means exactly the kind of dual thing. So if I have M1 to M2 to M3 to 0 is exact, so that one's a surjection, epimorphism, whatever. Here you're exact in the middle. Then when you take coinvariants, you're still exact, but if the first one was not an injection, then first one was an injection, then even still, the induced map on the coinvariants need not be an injection. Okay. And so again, I'll leave it as an exercise. Again, just very straightforward exercise that this functor is right exact. And as for the failure of left exactness, I think I'm going to use the same example. Yeah. If you use the same example and you take coinvariants, let's see. Well, when you're trivial, the coinvariants are yourself, just as the same way as when you're trivial, the invariants are yourself. So ng is equal to n. And yeah, if you think this through, then the coinvariants of m really are m mod n. Okay. And so, right, and so this time when you take coinvariants of your same short exact sequence, just, one-dimensional vector space into a two-dimensional vector space into the quotient one-dimensional vector space. This time you get n goes to m mod m, which are the coinvariants of m. Then you go into the coinvariants of m mod n itself, but m mod n was trivial, so again is equal to its coinvariants. Right, and so you get this sequence, and then you see that, yeah, so this, let's see. Yeah, so you see that this much of the sequence is exact. That's fine. On the other hand, we started out with an injection from n to m, and the map from n into m mod n is once again the zero map. Okay, so n and m mod m are still two one-dimensional real vector spaces, so the zero map between them is not injective. Okay, so the same example works. All right, and so now we can define group homology. So I guess I'll just define group homology, and that'll be the end of this lecture. So again, we do the homological algebra thing. So if you have an abelian category where you have enough projective objects and you have a functor into, let's say, Z modules, for instance, which is what we do, then you can define left-derived functors of your right exact functor by taking a projective resolution of your guy and then stripping away the m, applying the functor, and taking the homology. Okay. So the nth group homology of the group G with coefficients in the G module M is the homology of the complex where you strip away the M and you take the invariance. Okay, so it's the kernel of Dn modulo the image of Dn plus 1. And then once again, we have a short exact sequence is going to induce a long exact homology sequence. I didn't write this very clearly, but it's this, whatever the long exact homology sequence always looks like. It's kind of it's infinite in the other direction. So now this is, when we applied the functor, this one doesn't have to be injective anymore, so this one doesn't have to be 0, and then you have this whole sequence of homology groups, which is, correcting the failure of an injectivity there. Okay, so that's group homology and group cohomology. Yeah, so I think this is the end of the lecture. Good. So yeah, so the thing though is that like this is just if you like this, I mean, this is what it is, but it's a little unnecessarily abstract. The problem here is that in order to compute group homology or group homology, according to this, every time I see a G module, I have to compute a projective resolution and or an injective resolution. What a drag. Okay, and so that's not necessary. Okay, so we'll see later what we can do instead. Okay, so we do not need to do this. There's something called the standard chain complex and standard cochain complex that you can use to compute group homology and group cohomology. So whatever it is, I mean, it's you still have to mess with it or whatever, but it's much more concrete than take some projective resolution or take some injective resolution. And then the key thing that we need to do for the next lecture is, remember at the beginning of this lecture, I was blathering on about modules over the group ring ZG. And so it's not a very difficult fact at all. I'll let you think about this and come back to the next lecture, is that there's a categorical equivalence between G modules and ZG modules. Okay? So every G module